In this tutorial, we're going to look at the idea of the sum of angles. In fact, we're going to prove that the sum of angles in a triangle adds up to, or is equal to, 180 degrees, which is a really useful theorem that we're going to use later on to work on more advanced circle theorems. So let's write down what it is that we're going to do. We're going to try and prove, we want to prove that the sum of angles, so we use a symbol for angles, is equal to 100, in a triangle I should say, in a triangle, because only in a triangle will this be true, so in a triangle the sum of angles is equal to 180 degrees. Okay, so that's what we want to try and prove. What exactly do we mean? Well, let's first of all draw a triangle then. Okay, so two lengths and then join these up. And the sum of angles simply means if this is x, so if this is the measure of x, okay, let's draw it like that, and this is y, and this is z, then x plus y plus z will equal 180 degrees for all triangles in every case. So that's a useful thing to prove. Why is it definitely the case that the sum of the interior angles of any triangle is equal to 180 degrees? Well, there's a couple of ways of proving it. What I want to do is focus in this tutorial on the idea of exterior angles. The exterior angles will sum to 360 degrees. And if we know that the exterior angles of any polygon, in fact, will sum to 360 degrees, we can use that idea to prove that the interior angles will sum, in the case of a triangle, to 180 degrees. Okay, so to do that, all we need to do, once we've drawn our triangle, is produce all three of these lines, which means to extend them. So I'll produce it in that direction for this one. Let's go down here. Let's produce it down here. And we end up with this kind of spiky shape. And the reason why we need this shape is because we can now see very clearly, I use a different colour pen, we can now see very clearly that as well as the interior angle, we've now got the exterior angle here that we can work with. And this, if y is the interior angle, then this is the exterior angle for y. And if z is the interior angle, here we've got the exterior angle for z. And so what I'm saying is that the three angles here, they must add up to 360, in other words, a full revolution going all the way around. And why is that the case? Well, we need to first of all then show that that's true, and then if we accept that that's true, we can finish with our proof. So, what I like to do always is to label up any diagram. So we've got A, B, C vertices, let's say, and if we label these points here D, E and F. Okay, and that just helps us explain to anybody who's going to look at this work exactly what we're talking about. It's an easier way to refer to everything. Okay, so what I'm going to do now is make a point. Okay, so let's make a point, let's say here. And we know that the angles around a point, okay, will definitely equal 360 degrees by definition. So that's a kind of axiom, if you like, of geometry, that if you go all the way around, then you've got 360 degrees. So if I take DA, the line DA, and redraw it parallel to DA, draw another line parallel to DA, coming from this point, so like this, then I can do the same for all these other lines. So if I take CF, draw that parallel, and another parallel line EB, then I hope you'll agree that the three angles made by these lines must add up to 360 degrees because it goes all the way around. Now, if you've got parallel lines, then you've got corresponding angles. So the angle that corresponds to this one here, DCB, the angle DCB, the corresponding angle, which must be the same, is this angle here. The corresponding angle to EBF, this angle here, the corresponding angle is this one here. And finally, the corresponding angle to this third angle, EAD, well, the corresponding angle, if you look at the parallels, the corresponding angle is here. So we have gone all the way around, and that's the easy way really to show that we must have 360 degrees. If you want a visual demonstration of that, it's a good idea to stick some coloured paper snugly into these gaps, like that, and just move those onto our diagram here, and again you can see they're going to fit exactly. Okay, so that should be sufficient to prove that fundamental idea that the sum of angles around a point is 360 degrees, and therefore, because what we've done here is just kind of expanded out from the point, we've got the same idea here and here. The exterior angles also sum, just like angles around a point, to 360 degrees. They make a full revolution. Right, now that we've got the idea that the exterior angles of any polygon, in fact, will always sum to 360 degrees, we can use that to demonstrate or to prove our sum of angles theorem. Okay, so how do we do that? Well, it will be a good idea first of all to define the interior angle against the exterior angle. Now the exterior angle is this angle here, which must be halfway round, so 180 degrees minus x. So that must be 180 degrees minus x. So let's start there. This angle here must also be 180 degrees, so angles on a straight line minus y. And this angle is 180 degrees minus z. The reason, if we are setting this out a little bit more thoroughly than I'm doing here, the reason would be angles on a straight line will always sum to 180 degrees. And in part B, perhaps we'll have a look at how that can be proved. Okay, that basic axiom. But for now, we've gone a long way to proving our sum of angles theorem, and let's just complete the proof. So to write a proof, what we want to do is write it down very clearly. So we've got now our diagram labelled up, so let's use those labels and start with this angle here. So we know that the angle DCB, plus the angle EBF plus the angle EAD, add those together and they must add to 360 degrees. Reason? Angles around a point. I'll just symbolize that like that. Okay, now we can fill in our values or our little algebraic expressions here. So we've got angle DCB is 180 minus x. Added to that we get EBF, which is 180 minus y. And finally we've got 180, EAD is 180 minus z. And we know that those three angles sum to 360 degrees. 180 plus 180 plus 180 is 540. Minus x minus y minus z And if we rearrange that, subtracting x plus y plus, so adding x plus y plus z to both sides will cancel from the left-hand side, and subtracting 360 from 540, giving us 180. Rearrange, then we get x plus y plus z, the sum of angles, is equal to 180 degrees. That's what we were asked to show, so we need to just note that this was that which was to be shown. And that's how to complete a simple proof. We've proved now, we haven't just used this idea and accepted it, we've proved now what we set out to prove, that the sum of angles in a triangle is 180 degrees. So we can say we've proved the sum of angles theorem. Okay, now what we're going to do is use that theorem to work on some exam style problems. And what's the sort of problem that we might get? Well, let's start by showing how we can generalize this. So I'm going to now show that generally, this is a very useful idea, that the sum of angles in any polygon, so not just in a triangle, is equal to this 180 degrees times the number of sides, which will also give us the number of interior angles, so the number of sides, which we'll call n, take away 2. So what we've got is a formula, and we want to show that that formula must be true. Now, to show something, we don't necessarily need to prove it, but what I'm going to do is show a couple of cases. So let's draw a circle to begin with, just as a kind of template, and I'm going to cut the circle from here and just extend it so that we get exterior angles. So cutting a circle with a line gives us what we call a secant. So if I cut across like that, one more time, like that, and what we've got now is a quadrilateral, so a four-sided shape, four-sided and four angles. And what I'm hoping is that the sum of angles will add to 360 degrees. Why? Because we've got four sides, so n equals 4 minus 2. 4 minus 2 is 2 times 180 gives us 360 degrees. So these four angles should sum to 360 degrees if my formula is correct. Now, to show that, let's go back to this theorem. So the theorem says that the sum of angles in a triangle is definitely 180 degrees. That's been proved. So now let's use that to work on this, this quadrilateral. Okay, so first of all, it's a good idea whenever you're doing something like this to add a couple more lines. In this case, just one more line is needed to turn our quadrilateral into two triangles. Okay, now if we use a little bit of algebra, we can show that the sum of angles will add up to 180 times 4 minus 2, in other words to 360. So if we just label up our triangle here ABC, we can call this one X, Y, Z. What are we trying to show? That this angle here plus this angle here plus this angle here plus this final angle, all of these angles add up to 360. Now we know that A plus B plus C adds up to 180 degrees. We just notate that in there. And X plus Y plus Z add up to 180 degrees. What we've got here is this angle is A plus X. So angle, let's put angles in a triangle, in a quadrilateral rather. Let's just write a quadrilateral symbol like that. So angles in this quadrilateral must be a plus x, that's the first angle. Second angle is b. The third angle is c plus z. And the fourth angle is y. Now we can commute all of these. So in other words, rearrange them so that we've got a plus b plus c plus x plus z plus y. And we know that a plus b plus c is 180 degrees. And we know that x plus z plus y must also be 180 degrees. Reason? Angles in a triangle sum to 180 degrees. Therefore, angles in the quadrilateral must sum to 360 degrees. And that's what we set out to show. We could do that as well for a more complex shape. So very often we get something more complex than a quadrilateral, and let's just do it again so that we can see exactly how this works. So once again, let's just redraw our diagram. Okay. So redraw our diagram, and this time let's cut off smaller segments. So starting again here, working around our circle, and finally bringing it home. So what have we got? Well, again, let's use the sum of angles in a triangle idea and join from one vertex all the way around our circle, creating a pattern of triangles. Again, we know from what we did just now that if we add these together, we'll be adding together 180, 180, and so on until we go all the way around. So let's count how many triangles we've got instead of just adding them together. We've got 1, 2, 3, 4, 5. So in this shape, which is 1, 2, 3, 4, 5, 6, 7, it's a heptagon. So we can say sum of angles in a heptagon, so it's shaped like a kind of irregular 50p piece, like this. Sum of angles in a heptagon is equal to the 5, 1, 2, 3, 4, 5, 5 times 180 degrees. And 5 times 180 degrees is 900 degrees. And so we've got the sum of angles in a heptagon is equal to 900 degrees. Well, that makes sense. If we go back to our formula, the number of sides, let's just use a different pen, the number of sides we can see in this case is now 7. 7 minus 2, so we take off 2 and we get the number of triangles. In other words, we get this 5 here. 5 times 180 gives us our 900. So it's a nice little formula. You don't necessarily have to memorize it. I think it's fairly easy to remember. And even if you don't memorize it, you can just divide your polygon into triangles and use the sum of angles theorem. But if you can remember the little formula, then you simply subtract 2 from the number of sides, and then you get the number that's remaining. So the difference between the sides and 2 is 5 in this case, times 180 gives you sum of angles in this case a heptagon. So nice, simple, very, very quick, and a very, very useful idea when it comes to exam questions. Now let me show you why. If, for example, we had, let's say, this kind of setup where we've got x, let's say here, and let's say we have y here, and we're told that y equals, let's say, x plus 10. And finally, let's say they were asking us to find z. So we're trying to find 3 angles here in this diagram. Now it's an irregular heptagon, so if we have, let's say, 110, let's make that a little, that looks a bit small, let's make that 120. Okay, so let's say they give us 120, 125 they tell us is this angle here, 115, whoops, let's say here, and 120, 130 to complete. So all we need to do is form an equation, knowing now, as we do, that the angles, all of these interior angles, must sum to 900 degrees. Okay? So let's first of all take our variables. So we've got x plus 10 plus x, so we've got 2x plus 10 plus, now we need to go to one side to sum all these other angles. So what have we got? In fact, why don't I go in the middle? 115. Let's give ourselves plenty of room, so I put the 120 up there. 130. Now, 125 and 120. So that's all of these angles here. Have I got the right number? 5. 1, 2, 3, 4, 5. Okay, so adding down, we've got 10. Now I need to do a check, so I'll go up and down. So 2, 3, 6, 8, 10, 11. So 11, just checking. 2, 4, 6, 2, 4, 7, 8, 10, plus the 1 is 11, so that was correct. 1, 2, 3, 4, 5, plus the 1, 6. So we've got 610. Okay, so going back to our formula, we've got 2x plus 10, or our equation rather, plus now 610, we now know is equal to 900 degrees. Okay? So, let's resolve this. We've got all of these are degrees. So we've got 2x equals 900. Subtract 620 then from both sides. Like that. And I've got now 2x equals 180 degrees, actually. Does that sound right? Ah, no, 280 degrees. That's better. Okay, so just a quick check and you'll find your mistake. So 280 plus 620 is going to give us 280 degrees. Okay, so x is going to equal 140, so 280 divided by 2, 140 degrees. Therefore y is 140 plus 10, 150. Finally, we can calculate z. So z is the exterior angle. Again, angles on a straight line sum to 180. So z equals 180 minus 150 equals 30 degrees. So finally, what we want to do is just check that we have proved all our axioms, postulates and theorems so that we're building on solid foundations. And there's a couple of things that I just really skated over rather too quickly. The first is, I think, that the theorem that the angles on a straight line must sum to 180 degrees, which we were assuming. It's often taken as what's called a postulate, which is a theorem that you don't really need to prove, that's self-evident, we might say. However, I think it is worth having a look at that, and certainly taking it back to some basic axioms of geometry, which include parallel line ideas. Now, let's start then with a line, and at the end of the line, what I want to do is mark a point. Now I think it is clear that the angle all the way around like this must be 360 degrees. So the angles around a point obviously sum to 360 degrees. But how do we show that the angles on a straight line sum to half of that, 360 degrees in half? In other words, 180. Well, I think the easiest way is to just produce a line which is parallel, you can say, but also collinear. It's lining up. And if that line is collinear, then what we've done, as you can see clearly here, is we've bisected the angle all the way around. Therefore, the angle on both sides here must be 360 divided by 2, because this angle is being bisected, and on this side therefore also 360 divided by 2, which is 180 degrees. 180 degrees, of course, is two right angles, so sometimes in very old theory you will see it expressed not as 180 degrees but as sum of angles on a straight line is equal to two right angles. 90 plus 90, 180 degrees. So the theorem that the angles on a straight line made, for example, by one line just divided somewhere here, the angles on a straight line sum to 180 degrees is based on this idea of bisecting the full revolution. So we can say here that x, we don't know what that angle is, and y, so using algebra, x plus y must sum to 180 degrees, and the reason, angles on a straight line. So that theorem is proved and sound. Okay, so that's angles on a straight line adding up to 180 degrees. The other theorem that we've been looking at, and that's the main topic that we've been looking at in this tutorial, is the idea of a triangle, that the sum of angles in a triangle is equal to 180 degrees. So again, what we want to do, let's just erase this, is draw a triangle, and we're going to prove it now in a slightly different way. So this time, let's use the parallel lines idea again, but this time not collinear parallel lines. I'm going to draw a line parallel to, well, let's call this A, B, C. So I'm going to draw a line parallel to BC. So we can call this DE. So we say BC, first of all, before I do that, let's say what are we setting out to prove? So we're setting out to prove that, well, let's label these up, X, Y and Z, that, do I like it labelled like that? Let's put Y there actually. Okay, let's go round anti-clockwise, so X, Y and Z. So, doesn't matter, but I just like it lining up in this way. You'll see why in a moment. X, Y and Z sum to 180 degrees, so we've got to prove that X plus Y plus Z equals 180 degrees. Okay, so now we can say that we've got our two parallel lines. So I can just use a symbol here, or I can say that BC is parallel to, so use a symbol here, parallel to DE. Okay, and from that basis we can work on not just these angles here but also these angles here. So the basic idea with a proof is fill in all the angles and then you should be able to finish the proof. So what about this angle here? Well, this angle here has got to be equal to this angle here by one of the basic axioms of geometry, the idea of alternate angles. So BC A, angle BCA, is equal to angle CAD, and the reason is alternate angles. Alternate angles are congruent. Now you may have already learnt this and be familiar with this. There is another way of doing it. Let's have a look at angle Z for an alternative way of showing that. So angle Z, well, the alternate angle to angle Z which is ABC, angle ABC, that must equal this angle here, which is angle EAB. Same reason, but if we're not sure of alternate angles and we just wanted to prove it, here's a very simple way of not relying on the idea of alternate angles between two parallel lines, and that's by adding or just producing this line just a little further. So if we produce it down to here, we can see that we've now got very clearly corresponding angles. So can you see that this angle here, ABC, if we call this, oh, no, let's call it F. Okay, so ABC has got to correspond to FAD. In other words, this angle here. Just to make that clear, let's just use a double angle symbol. So these two angles are corresponding. And why? Because we've got two parallel lines, so you can imagine just moving that angle along to there, just sliding it along, their corresponding angles, and that's axiomatic. Okay, foundational kind of idea. So if this is Z, so if this is Z down here, because it corresponds to this angle Z here, then we can also say that we've got a straight line here. So this must be 180 minus Z, this angle here. And if that's 180 minus Z, well, we've got a straight line here. So this must be 180 minus Z. Okay, and if we remove the brackets, that's going to be equal to, well, the 180s cancel, and we've got minus Z, which is just Z. So what we've got here are what are known as vertical angles. Okay, so this angle and this angle are congruent. But again, we haven't just assumed that vertical angles are congruent. We've actually proved that vertical angles are congruent, which is another way of proving the alternate angles, that alternate angles between two parallel lines, they will be congruent. So Z equals Z here. Okay, so what have we got now? Let's just say them. So we used corresponding angles, say angles, and we've used vertical angles to show that we've got alternate angles again between two parallel lines. So now that we've worked all of that out, systematically we can say that X and X, Z and Z, we've now got at the bottom here 3 angles on a straight line. So therefore X plus Y plus Z are equal to 180 degrees. Put the reasoning brackets, angles on a straight line. And X plus Y plus Z, the sum of the interior angles, was what we set out to show. So it was that which was